Hi everyone, I'm Dom again. Jakob asked me to speak about Clojure today. Clojure is... Sorry, can you not? Okay, I will project. Jakob asked me to speak about Clojure today. It's my favorite language at the moment. It's a Lisp. I'll show you some Clojure code. It will look scary, possibly. This is what it looks like. Huh?
Could you please make the font bigger?
Maybe. I don't actually know how to do that.
Control plus plus.
This is Emacs. I don't know if that works. No, it does not.
It will be Control Alt butterfly.
You can just zoom in. On Macs, you can just zoom. No.
But just you need to see the other windows as well.
All right.
You know what? Hold on. This is a great beginning. Okay.
Okay.
Control is control plus.
What?
Control is control
Sure,
plus.
Super. Thank you.
Is this good? Is this good enough? Let's see. Okay. I apparently have to do it in every window separately. Or every culture separately. Alrighty. So, when we talk about Clojure, Clojure is a Lisp. It comes from a different family of languages than Python, Ruby, or JavaScript, or Java, obviously. Those are the primary languages I've heard. I'll try to contrast it to Python and its Ruby a bit and JavaScript a bit as I go. I didn't really know what to talk about with this because it's a very large area to introduce someone to a language that they haven't used before. So I'm going to talk about concurrency and parallelism in Clojure because it's a particular strength of the language. And I was inspired by a problem we were having in Ruby Storm, which certainly for me when I was working in Ruby was a common problem. And I believe also is in Python as well, which is dealing with things easily in parallel without blocking. This, as I said, this is something Clojure excels at. Okay, a bit more about Clojure. Let's see. It is hosted. Clojure is hosted on the JVM, so it compiles the JVM bytecode. Clojure script is a dialect of Clojure which compiles to JavaScript, highly optimized JavaScript. They are almost identical, aside from the host-ish interop. You can drop down to Java whenever you need it, or drop down to JavaScript whenever you need it. But for the most part, we can write the exact same language and work in both environments. Obviously, one of them is not actually threaded, but you can still work in the same paradigms. Anyway, I guess let's get going with this. Oh, and if I don't speak loud enough, or if I say anything confusing, or just interrupt with any questions, whatever. Okay, so we're going to go through a few little basics. I'll try not to go too crazy with them, but they'll be necessary later on, and we'll do a little bit of concurrent and parallel things. Okay, so this is a namespace, Pražské Pyvo, July. Hope I pronounced that correctly. We're using, I believe, Python has imports.
Can you maybe select the thing because the cursor is very hard to see?
This.
Yeah, now we can see it.
Okay. So like this whole form up here, from NS to here. Can you see that?
Yeah.
There we go. Okay. So this is a namespace declaration. We're saying this is the namespace that we're in. Python, I believe, has namespaces, and you can import things. Correct me if I'm wrong. I don't know Python really. Is that right?
That's correct.
Correct. Okay. So this is just very similar to that. Ruby doesn't really have that. We pretend we do with modules. JavaScript definitely does not have that unless you, not natively, although in this instance it does. Okay, so this is essentially the syntax most of you are probably familiar with. You have a function, you have arguments that get passed in either implicitly via white space or wrapped in parentheses. In the Lisp family of languages, the function name is the first thing in the parentheses, and the second, third, fourth are the arguments. That's pretty much all you need to know when you're reading this code. There are some intricacies that change things, but that's the main difference in syntax. Okay, obviously Clojure has the basic types like root, strings, numbers, etc. So I'm going to skip those. We'll just talk about data structures, the basic ones. Clojure has lists. These are, I don't know if you can see this, but over the bottom right hand, I'll be evaluating stuff and they'll be appearing either in the bottom right or right top. So a list in Clojure is a linked list. It's not like a Python list. Ruby and JavaScript do not have these. I don't know if Python does. Clojure also has vectors. A vector is like a Python list, or a Ruby array or JavaScript array. The difference in Clojure is that everything is persistent, which is commonly called immutable. So this vector that we've defined as, I should have said def. Def is defining something. That was probably obvious. Okay, so we have this vector called a vector. It is immutable. You cannot change it. However, that's not really a useful feature in and of itself. You need to be able to pretend you're changing it. So you can, say, conjoin something onto it. In this case, we can conjoin D, and we get back a vector that looks as if we changed it. However, if we go back to the previous one, it's still the same. This is, in Clojure, extremely performant. You can drop down to mutable versions if you need to in specific cases, but in almost all cases you will use immutable versions. They have, this is probably my favorite thing about the language. It doesn't sound like it would be originally, but it is a huge relief if you've gotten used to encapsulating state to not have to worry about anyone fucking with your state. You can just pass around data freely, and you know that it will not change. It allows you to program in ways which you can't really imagine doing otherwise. It's also an extremely useful feature when you're working with multiple threads, because you can safely share data structures without going through headaches of mutexes and locking and synchronizing threads and things like that. So being able to just pass around a single object and know that it will never change no matter what for the life of the program is very useful. And we'll see a bit more about why later. Okay, so Clojure also has maps. These are like Python dictionaries or Ruby hashes. JavaScript does not have them. They are also persistent, as we said. So this says key 1, val 1, key 2, val 2. We can associate a new key 1 value in there. So we have new val 1. Yes?
I saw comma in the output. Can I write it in the input to
Good question. You absolutely can. Commas are white space, which is awesome, except it sucks when you have to go back and write JavaScript or Ruby or something like that, which I frequently do, because it is the most common error I make by far. But yes, comments are white space. They do get printed if you're printing something, but they're just white space. Typically, if you're doing something like this, you would actually do new lines for each pair, and that's how you separate them. Okay, excellent question. Anyway, so we can associate a new value in here, and if we go back to the map that we've defined, it's still the same. So when we call this function, we just return a new map with the change there. Clojure also has sets. These are like Python sets, Ruby sets. Again, JavaScript does not have them. Surprise, surprise. Okay, Clojure is a functional programming language. Functions are first class. They're the primary construct for doing things. Don't know how else to say that, sorry. This is how you create a function. So we're creating a function here that is squaring a number. defining a named function is such a common thing that there's a special form for it, which is defn. So it's like def plus fn. So we can create a function called square, and then we can call it with the number we want, and we get the result.
What's the hash for in the set definition?
What is
The hash mark?
Syntax for set.
Oh yeah, so this is a map with just curly braces, right? And then if you put a hash before, it's a set. So every single one is a key instead of just every odd one or every equal. Yes, sir.
Is there a functional difference between what fn produces and what defn produces?
No.
Is the code for the function the same?
Yes. This defn square is for 90. It's technically
It's just
there's
a
technically
name.
a slight difference, but it's basically the same as def square fn
Yeah.
x.
So it's a shorthand for. It's nothing to do with lambda or anything like that. It's just shorthand for.
Yeah, it's a very common thing you have to do. There are slight differences in some of the more advanced usages, but it's all of this is things. I won't go too deeply into this, but one of the very cool things about this are that any of these things are things that you can do yourself. So defn, def, these are things that you could write yourself.
So they're functions.
They are functions, yes, essentially. Or they're macros technically. They hook in. Let's not go into this. This is very complicated. Anyway, okay. So having a language where you cannot change anything is totally useless because, well, our program enters and exits and nothing happens. So Clojure is not against mutation; it's against rampant, uncontrolled mutation. Obviously, we do need mutation in order to do something, which is the goal. We just want to control what we're doing. So Clojure has a bunch of primitives for controlling mutation. I'm not going to talk about all of them because there's too many and some of them are very complex, but we'll talk about the very, probably the most useful and the most basic one, which is an atom. An atom is basically like a box, and as you see, I've defined this one as box. It is, so normally you have maps, strings, whatever, they're immutable, and they have the same identity as their value. So the identity of this map is the same as what it evaluates to, like if you compare it to something else or like modifying it or anything like that. An atom has different identity and value. So it is, you could have an atom called Tom or something, and this is like this is an entity, right? But the value that's inside it can change over time. So this is the closest thing that we have to a variable, basically. They are very useful because obviously you need to change things, but this allows you to do it in a controlled way. So you can observe changes, you can listen for changes to this thing, you can access it from multiple threads in parallel, you can read in parallel, you can have only one writer at a time, so it's very safe to like share this mutable thing across threads without any additional work. And we can, so the at symbol before the box, that's called deref. That's like taking the thing out of the box. So if we deref it, we get foo. If we reset it to bar, then if we deref it again, we get bar. So it's changing the values inside of the variable. Okay. Seeing all the params, you might be getting a little scared if you haven't done like Clojure or Scheme or anything before. Imagining things, like this, which is incredibly ugly. A lot of the code later on that I'm going to show you will look a little like this. And the reason is because there are more advanced things in Clojure that you can use to make your code a lot more readable and elegant. But they are not easy to digest and explain, so I'm going to skip them. But here's a very basic example. So in this case, we are taking a range to 100, then we're going to increment every single integer in there, then we're only going to keep the even ones, and then we're going to take the sum of the total. This is probably definitely a much more idiomatic way to write this in Clojure. It reads the right way, you don't get a huge stack of friends at the end. Very easy, right? So don't be afraid of friends. There are a lot of tools in the language that make them really easy to deal with, and I believe much better because the code is actually all data structures, so your editor can manipulate it like a data structure, which is pretty awesome. So that's all I'm going to go into that. But generally, with like production Clojure code, you won't have more than like 3 friends at the end of anything, so it's not a big deal. Okay. This is something you don't need to see. I just need to do it to get some sort of safe logging. Okay. So there's a part of Clojure called Clojure Core. Actually, let me do one. How many people here have done anything with Go?
Sorry again?
Anything with Go, the language? Nope? Okay. A little bit. All right. So Go has this really cool feature called Go routines. They are based on a paper from like 78 or something. It has all good computer science concepts from that was called communicating sequential processes. The concept is that you have channels, and those channels are like very, 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 very lightweight threads. Threads / queues. And you can put things onto them and take things off of them. And you can write code in this way that looks synchronous, but behind the scenes it gets transformed into asynchronous, generally non-blocking code.
Maybe if you could ask differently, who knows yield from in Python? Because this is more relevant and it's the same concept.
All right, but is that blocking?
No, it's coroutines. Just built into Python. Recent version of Python.
Interesting.
With yield from.
Okay.
Delegate to coroutine.
Okay. Cool. I'd like to see it.
It's a different kind of code.
Okay. Fairly a bit different. Anyway, who knows yield from? Yield from might be similar to this. I'm guessing it's not super similar because I haven't heard of it.
It's too new.
Okay. So the basic concept is you have these channels. You can put things on, you can take things off. You write your code in a way that looks like it's synchronous and blocking. However, in the background, it gets transformed into non-blocking asynchronous code. Guys, gosh. Okay, so we'll go through a few examples here, and then we'll go through a more real-world-ish example. Okay, so Chan creates a channel. Let is like a local variable binding. So we are going to bind the variable C to a new channel. Then for every integer in this range, we are going to have 2 go loops, or go blocks. I probably should have said that Clojure stole this concept from Go, which is why I brought it up. It works in both Clojure and ClojureScript, so you can write the exact same code and have it work in ClojureScript in a single-threaded but non-blocking way, which looks linear, but in the background becomes callbacks. And in Clojure, you write it the same way, but it gets transformed across multiple threads in the background, and also non-blocking within those individual threads. Okay, so in this case, we're saying Go returns immediately, so it proceeds on to the next Go, which also returns immediately. What happens inside of this is that we take a random integer up to 100 or up to 1,000. These are milliseconds in this case. We're then creating a channel with timeout that will close after that amount of milliseconds. We are then taking something from the channel. That's what this less than band is. So what happens here is Go will wait right here at this take until the channel either has something in it or closes. It doesn't stop this Go from running, remember, because Go exits immediately. But this line here, this will not run until timeout closes. So this is like thread sleep. or whatever the alternative is, but non-blocking. We're not blocking any thread right here because it just queues it up into the background and moves on, or moves on with that thread. Once this timeout does close, once this timeout channel does close, then this takes nil from it, which means that it's allowed to proceed on to here. The greater than, I believe, bang, then channel, then integer means put this integer onto the channel, right? So then we have this go loop right here, which is just listening for things coming onto the channel. When something comes on, it takes it off and it logs it to output. So if we run it, we see that we get, so zero, I should actually just evaluate range. So this is what we get from range, 0 through 9, right? The reason it's out of order is because this is all happening asynchronously and we're waiting for some indeterminate time of up to a second. Okay, so, yes?
And the memory space is short for all the... the memory space is short for all the proteins?
Yes. You can pass it back and forth between them.
So basically, you're starting to be memory bound with regards to...
I'm sorry,
you're starting to be memory bound with regards to memory.
You're starting to be memory bound with what?
As in you accumulate all the memory from all the routines.
No, I mean they get garbage collected after they run.
Immediately.
I mean it depends on the garbage collector.
Okay.
You can't like manually free space in JavaScript. Okay, so yeah, but it's not a memory problem. They just it gets turned into a state machine in the background and with callbacks. Like it's Go is like a never read the source for Go. It's like 300 lines of absolute insanity. Okay, but awesome insanity. Okay, so I talked about how data structures are persistent, aka immutable. Very useful when you're sharing stuff between all these threads and stuff like that. Also with atoms, you can share them easily. So in this case, we're doing almost the same thing as the prior version, except we're also assigning v to be a vector inside of an atom. The reason we're doing this is because instead of just logging each number as we get it, we're going to add it into the vector and modify this data structure in parallel. So technically we're not modifying it in parallel, but it will attempt to be modified in parallel, and any collision will just be retried until it works, because there's no mutation within any individual instance of that vector. Sorry, that got a little confusing. Anyway, you'll see what I mean. So, in this case, we go 3, 8, 4, blah, blah. So this is just each time it runs, we're adding one more to the end. And that doesn't modify any of the previous ones. If we run it again, we get new output. Okay. So that's the basic. Core async is pretty low level, and there are a lot of very useful abstractions built on top of it. I'm not going to use any of those for this. I'm going to talk about, I did do like a very little real-world-ish example from RuneStorm. So the thing that inspired me to do this particular topic about Clojure was that we're calling out to this evidently pretty crappy API to check for room availability. So we'll call it like a room provider API. A call to it can take like 5 seconds. So the backend needs to be able to deal with like having multiple requests for rooms from the front end from clients, and not fail when there's a small amount, because it can't complete each request in a serial fashion if there are too many requests, right? So, and this is obviously a big problem I have in Ruby as well. So what I did here is I built like a very, very basic example of how we would do something with Clojure that could serve thousands of concurrent clients, because the problem is inherently I/O bound, and if we don't block any thread on I/O, then we can deal with lots of concurrent clients, right? Because we just like most of the time spent waiting when the client sends a request, you wait there, you send something out to this room provider, you wait there, and if you don't block any threads, and those threads can go work on other clients, you can do a lot more. Okay, so a few little helpers here. We have this hotel IDs, that's just A through F, or I guess A through E, which we'll just use for hotel IDs. We have a helper function to provide random hotel IDs. So if we call it repeatedly, we get different IDs. We have a fake API wrapper function called really slow request rooms. We give it a hotel ID, and I'll show you what it does. Okay, so I haven't talked about this yet, so we'll talk about it now briefly. Clojure has something called a promise. If you've been doing JavaScript, you probably know what promises are. I don't think I've seen the promises much in Ruby or Python. A promise is like, I'll use the box metaphor again. If I give you a box and I say, I will eventually put something in this box. And as long as you hold on to the box, you don't know when I'll put the thing in it, but I eventually will put it in. So you can just hold on to it and just keep checking it. You put something in the box, yes or no. Once he does, you can use the thing in the box. So it's a way of coordinating eventual values. If you want to give something back to someone immediately, but you don't know what yet, as in API request, where you want to return a response, but you don't want to block there, you can give them a promise or something like that, which will eventually have the response from the API. So in this case, we're going to return a promise. We're also going to start a go block here, and we're going to log that we are sending a request for this hotel ID. Then we're going to wait here, as before, for up to 5 seconds. Then we are going to log that we got a response back, which we didn't, but we'll pretend we did because this is not a real thing. Then we're going to deliver the promise, and we're going to say, like, we have some random number of rooms of up to, like, 41, right? So 0 to 41 rooms are available. And then we're going to return the promise immediately. So all this go stuff, that happens in the background. This function gets called, it returns the promise immediately. Okay, so how does that work? If we call it, why would we do this? Okay. Okay, so if we call it, it returns a promise immediately, and you see these got logged out here. If we call it, let's say 2 times, each one of them is going to wait for the next one, right? So then we have a quick little utility here that we'll use. We're going to memorize this function. So what we're going to do is we're going to say that if we make the same request, if we request the rooms from Hotel X within the last 2.5 seconds, just give us the previous promise, because they're probably still the same or close enough, right? And then if it hasn't been requested ever or in the last 2.5 seconds, it will make a new request, and that promise will be cached for another request. So if we evaluate this, and then call it several times, we'll only see that it gets logged once, because this function, this go block, only actually gets run once. The other times just return the promise immediately, right? Is everyone sort of at least following along? I feel like I might have lost people.
I do. There are promises, blah, blah, blah.
Does that mean that that when you make new requests that they'll get the same result?
Yes.
That's a problem, right?
It's not a problem. It is solving a problem. But it's a good question. It could be a problem if we need results to always check the API. But the likelihood of the room data changing in the last 2.5 seconds, as an example, is probably pretty small. So this will like if 15 requests come into our backend, then we don't want to have to launch 15 requests to this API that takes 5 seconds each, right? So we just ask it one time, and then those requests all get the same answer. Then we throw that answer away, and when we get a new request in, we ask again.
I mean, it's not a Clojure question, really. I guess it's a question about
Yes,
the way that you've implemented this, rather than a question about Clojure.
I would also,
it's not a Clojure question.
I would like to add that maybe for, I don't know, financial transactions, it's important if like price of the stock changes in the last 2.5 seconds, just a fraction of a coin, then it's a problem. But for us, it's not actually very important. So whether there are 10 rooms available or 9.
It's better to be responsive than to...
Exactly.
Yeah, it's just a caching issue. Like the domain you're working in will determine it. In some cases you can't cache at all. In some cases you can safely cache for like an hour. In some you can, if it's a static website, you're basically caching indefinitely, right? Yeah, so not a Clojure question, but a good question nonetheless. Okay, so we've got that memorize thing. Next we have a function called handle request. This is going to take a request ID and make quote unquote the actual request. So we'll go through it real quick. We'll start out with okay, all right. Good. We start out with a go loop as always, so that we're never blocking. This function, as all the other functions, returns immediately. Then we're going to do a local binding. We're going to get ourselves a random hotel ID, so that's A, B, C, D, whatever. Again, we wouldn't actually be doing it randomly. This is just an example. We're then going to log the beginning of this transaction and see what's happening. Then we are going to bind the result of the request that we just memoized above to rooms. So rooms right here is a promise, right? Okay. So then remember we're still in this go loop. So what's going to happen is we're going to say while the promise is not realized, that means if the box is still empty, if it hasn't been delivered, we are going to check. Excuse me. If the box has not been filled, we are going to wait here for 50 milliseconds. Then we're going to check again. And whenever it gets filled, we're going to move on. So that's what this while thing is. Then we're going to log the end of that handle event. Last is a function to just run the server. We're going to say we're getting 10 requests in at the same time. How do we deal with it? That's what we're doing. Okay, so here's how it works. So what happens here is we get a request in for hotel. The left arrow is actually we're going top to bottom, or bottom to top. The right arrow is a request that we're sending out. The left arrow is a response. It is either going out to hotels and checking availability, or it is a user that's coming into us and then going back to them. So we're immediately checking, we're getting these requests from users. We're going out to these hotels. You'll see that even if there are multiple requests for the same hotel, even if there are multiple requests for the same hotel, there will not be multiple responses from that hotel. Well, there shouldn't be. Let me dissect this and give you an example.
Can you clear it out?
Sorry?
Can you clear it out?
Can I what?
Clear it out.
Probably. That didn't really work.
So go ahead.
Alright, so where are we beginning?
Wrong.
I'm trying to figure out where this is beginning and give you a good example of what's like this. It's hard. I didn't really know how to visualize this. The basic idea is all these requests are coming at the same time. We're running on multiple threads. No threads are ever blocked waiting for any I/O. All threads are doing this computation and handing processes off to other threads. So
how does it work? So what Clojure has built-in paralleling thing?
No, that's the Go stuff.
Okay, that's good. Okay, got it.
So we get a request, we immediately return from the main thread, so we can keep handling more requests, right? What happens is that thread, they're not real threads, they're like Go threads. They're actually using multiple threads at the same time. That thread is also using multiple threads to check the hotel, which is waiting. And every time we're waiting for any I/O stuff, it just gets run in the background as a callback. We're never blocking any threads here. And
how's it better than Python?
Do you want me to beat up?
Yeah.
Yeah. Thanks.
I can do Lightning, not about that to do with Python.
All right. Okay.
Okay, I'm going to try to plug in some. Okay, so Hotel E gets requested from users 1 and 2, right? Then we make the request to Hotel E, we get the response back, and then we give the data back to users. Okay, this does actually work, but the output is really messed up right now. Anyway, I can restart it if you like. I don't really know how to solve this. I'm not really a guy.
Move on. It's okay.
Okay, that was essentially the end of it. Any questions?
I got it.
Do you promise it works?
I promise it works.
It works, guys.
Dumb in the box.
It's working right here.
So the first request that goes to a hotel.
I quite believe it.
So you've got the promise, right? Which is I know from .NET we have these new awaiting things. So we have a task, and an object is wrapped inside task generic. So it doesn't have the data yet. But
Yeah.
we can still pass that around as if it existed.
Yeah.
As the type that it is, and then when the job is finished, the moment we try to reference it, it will block until that's ready. So that's what a promise does.
Yes.
I take it right.
Exactly.
So the first user who requests a hotel, they will wait the longest because they have to get that data.
So what depends what you mean by wait. In terms of clock time, they will wait the longest, but they will not be blocked.
Well, what do they get as a result? They get a promise.
They get a promise, but
The user gets the promise.
I'm not sure what that means.
Well, you wouldn't give a user a handle to data that isn't there yet.
So you give them a promise. Is that what you mean, a handle?
But what do they see as a user of on a UI? What do they get? If they're trying to.
So this is like the API layer.
Yeah. So at the user side, they just see spinning. They wait until this thing comes, and then when the hotel responds, every user that asks for that will get the response at the same time.
I mean, barring network failures or different speeds. Yeah, essentially. But again, this is not a real example. We're not doing any actual network activity. Any I/O here is just simulated by having a timeout.
Mm-hmm.
But essentially, yes. And while if we did dereference when the promise was not fulfilled, we would block. We're not doing that here, so we're not blocking it.
Yeah.
We're just checking if it's been fulfilled.
But you would block because the promise only exists in this environment. It doesn't exist. You don't send any reference to the users.
No.
They can't call back later with a hash or anything. And
that is a much larger concern than the language.
Yeah.
But an interesting idea. Good question. Anyone else? I think I lost everyone, sorry.
Thank you, Al. Thank you very much. I really